Welcome to the Explainer. Today we're looking at something truly mind-bending, a genuine marvel of modern physics and human ingenuity. I want you to picture this. The International Space Station is falling toward Earth right now. In fact, it's been falling continuously for over 25 years, and yet it has never, not even once, hit the ground. How is that even possible? Today we're going to unpack exactly how this works using some brilliant engineering principles, and we'll look at why the ISS is constantly fighting an invisible battle just to stay alive up there in the dark.
Okay, let's dive into this, because the absolute secret to this entire trick lies in one massive number: 17,500 miles per hour, which is about 7.66 kilometers per second. That is the incredible sideways speed the ISS is traveling at every single moment of the day. And that raw, staggering speed is literally the very reason it avoids crashing back down into our planet.
Which brings us to a massive question, right? How do you fall for a quarter of a century without hitting the ground? It sounds like a total contradiction, but actually it's not. It is the literal, scientific definition of how orbit works. But as we'll see in just a moment, there's a second, completely invisible threat hiding underneath this neat little physics trick, one that the astronauts and engineers have to deal with every single day just to prevent disaster.
Section 1. The paradox of falling. So, to truly understand how you can fall forever, we need to look back at an ingenious thought experiment devised centuries ago, long before rockets, satellites, or space stations were even a glimmer in humanity's eye. I absolutely love this concept. It's called Newton's cannonball. Isaac Newton imagined this exact scenario all the way back in the 1600s, centuries before anyone had the technology to actually test it. It's a thought experiment demonstrating that an object moving fast enough horizontally will continuously fall without ever actually reaching the ground. Just imagine sitting there in the 17th century and visualizing orbital mechanics perfectly in your head.
To give you that perfect aha moment, let's just walk through how this works. Step 1, you fire a cannonball horizontally, and gravity pulls it down into a normal arc until it hits the dirt. We see this all the time, right? Well, step 2, fire it faster. Now it travels much further before landing because the Earth's surface is actually a sphere, so it's curving away beneath the ball as it flies. And finally, step 3, you fire it at roughly 17,500 miles per hour. At this extreme speed, something magical happens. The cannonball falls toward Earth at the exact same rate that the Earth's surface curves away from it. Gravity never lets go of the station, it just never catches up. It keeps missing the planet forever.
Section 2. The invisible atmospheric drag. Now, you might be wondering, if the physics of falling are so perfectly balanced, why does the ISS need any help at all to stay up there? Shouldn't it just spin around the Earth until the end of time? Well, it turns out that space, at least at roughly 400 kilometers up where the ISS lives, isn't actually completely empty. The ISS faces constant atmospheric drag. This is the resistance and loss of orbital energy caused by microscopic collisions with stray oxygen and nitrogen molecules floating around in the upper atmosphere. You see, the ISS is absolutely massive. It's roughly the size of a football field, complete with these huge sweeping solar arrays and radiators. And even though the atmosphere is incredibly thin in low Earth orbit, it is still very much there. Millions of tiny molecular collisions constantly tap against the station. Now, each impact is totally meaningless on its own, but multiplied across millions of collisions every day, they steadily bleed off the station's crucial orbital speed.
So the crucial point is this number right here, 50 to 100 meters. Because of those tiny molecular impacts, under normal conditions, the International Space Station slowly sinks by this much altitude every single day. It's a slow, constant descent brought on by that atmospheric friction.
But here's the thing, it's not always a steady 50 to 100 meters. When the sun is highly active, it releases energy that actually heats up the Earth's upper atmosphere, causing it to puff outward. This thickens that thin drag layer the ISS is flying through, which dramatically accelerates the station's sink rate. During a strong solar storm, the station can drop by entire kilometers in a short span, rather than just meters.
Section 3. The counterintuitive reboost solution.
If left to that slow, daily bleed, the station would eventually be pulled deeper into the thicker atmosphere and be completely destroyed. So, engineers needed a clever, ongoing fix to maintain the orbit and fight back against the drag. Now, what's really interesting about this slide is how it challenges what you might intuitively picture. You'd probably imagine a spacecraft firing its thrusters straight down toward Earth to push the station straight up, kind of like pushing a boat directly off a sandbar, right? But what actually works is firing engines forward, precisely along the path of the orbit.
To do this, Mission Control doesn't even use massive thrusters built into the station itself.
Instead, they rely on vital supply ships, Russian Progress vehicles, SpaceX cargo dragons, and Cygnus spacecraft. I mean, it is honestly amazing to think about. We literally use space cargo trucks to push a football field-sized lab around in space. Every few weeks or months, mission controllers use these supply ships while they're securely docked to the station to perform these essential reboost maneuvers.
And here is how wonderfully counterintuitive this orbital maneuver is. Step 1. The docked spacecraft fires its engines forward, in the exact direction the station is already traveling. Step 2. This forward speed increases the overall velocity in orbit. But here is the real magic in Step 3. Adding speed doesn't just make the station go faster in place. Because of the mathematical shape of the orbit, it actually lifts the altitude on the completely opposite side of the orbital ellipse. So pushing forward translates into a higher altitude rather than a straight vertical climb. This exact principle governs every satellite, spacecraft, and orbital maneuver ever performed.
The incredible efficiency of this operation is just mind-blowing. A single reboost burn is surprisingly short. Just a few minutes of thrust literally buys weeks of margin. It's a true testament to the brilliant people on the ground at Mission Control doing incredibly complex math week after week, making tiny, precise corrections to keep this massive laboratory floating safely above our heads.
Section 4. A planned eventual retirement.
As amazing as this system is, it can't last forever. It has a lifespan. Now, you might be wondering, why not just place the ISS in a higher, drag-free orbit from the start and avoid all this reboosting altogether? Well, the answer comes down to pure logistics and cost. While a higher orbit definitely means less atmospheric drag, it would also be far too expensive and difficult for regular resupply rockets and crew missions to reach on a routine schedule. The station is deliberately kept in low Earth orbit, specifically so we can actually get to it.
The lifespan of the ISS is incredibly impressive. From the very first module launched in 1998 to today's regular reboosts, it has successfully defied gravity for decades. But its eventual retirement will end in a safe, controlled descent. The specific year is left deliberately vague as international transition plans and commercial space station projects continue to evolve, but the mechanics of exactly how it will end, those are already written in stone.
When that day finally comes, engineers are going to use the exact same orbital physics we just talked about, but flipped. They'll fire the engines in reverse. By deliberately slowing the station down instead of speeding it up, it will drop its altitude on the opposite side of the orbit. It'll descend in a highly controlled manner, ensuring it lands safely in a remote stretch of ocean, completely avoiding populated areas. The exact same physics that kept it aloft will bring it down on purpose, exactly when they choose to.
Ultimately, it all comes down to this single, beautiful phrase: a constant, quiet negotiation with gravity. The ISS doesn't defy gravity, and it certainly doesn't ignore the Earth's atmosphere. It survives through continuous, careful, human-maintained negotiation, falling fast enough to never hit the ground while getting exactly the right forward nudges from mission control to overcome the drag it simply cannot avoid.
Which leaves us with this final, provocative thought to ponder. We've mastered this delicate dance to stay in space, but what are the other hidden engineering secrets keeping astronauts alive up there? I mean, keeping the station in orbit is one monumental task, but keeping the humans inside it breathing in the vacuum of space is another entirely. If this connected the dots for you and sparked your curiosity, I highly encourage you to check out our previous explainer on how the ISS miraculously makes its own oxygen and recycles its water. There's just so much more to this incredible machine. Thank you so much for exploring with me today on The Explainer, and keep learning.